Welcome back to the deep dive. Today we are doing something a little different.
Yeah, bit of a change of pace.
We aren't looking at the shiny marketing slides from a product launch. We aren't looking at the Hello World tutorials that make everything look, easy and cheerful.
No, not at all.
We are looking at a stack of material that acts as a brutally honest, no-fluff reality check on what it actually takes to survive and thrive in the Apple ecosystem.
It is a reality check, isn't it? I mean, we often see the glossy keynotes from Apple, the promises of write once, run anywhere, and this idea that coding for an iPhone is just dragging and dropping a few boxes.
Right.
But the source material we have today is it's essentially a technical manifesto. It's a three-part guide on survival.
Survival is the right word, because when you dig into these notes, you realize we aren't just talking about syntax.
No.
We are talking about the massive, often painful gap between a junior developer, someone who just wants the code to compile and run on their own phone, and a senior developer,
A huge gap.
someone who wants the code to be scalable, safe, and actually shippable without getting rejected by the App Store.
Precisely. And that gap is where most projects fail. The mission of this deep dive is to bridge that gap. We're moving from the mindset of, it works on my machine, to this will work for 1 million users on different devices with bad network connections without crashing.
And to set the tone right off the bat, we have to talk about the walled garden. That's the metaphor everyone uses for Apple, right?
It is, and for good reason. The source material makes a really compelling point here regarding that philosophy.
Which is?
The walled garden is safe, it's beautiful, and users love it because it's curated and, generally bug-free. But for a developer,
It's a different story.
it's strict. It is incredibly strict. If you try to fight the system, if you try to be too clever or bypass the constraints Apple sets, the garden becomes unforgiving. You'll find yourself fighting the compiler, fighting the operating system, and eventually fighting the app review team.
So think of us as your guides through that garden today. I'm here to unpack the jargon and get to those aha moments.
And I'm here to explain why the gardener, or in this case, the compiler and the platform itself, is so demanding. I'll do my best to keep us on the straight and narrow.
Let's jump right into segment 1 then, the Swift philosophy. The sources start with a pretty bold claim, the lie of easy Swift. Apple markets Swift as safe, fast, and expressive. It sounds so friendly, like a scripting language you can just pick up on a weekend.
It does. The marketing makes Swift sound a lot like Python or Ruby, easy to read, very forgiving, very flexible. But the reality, as outlined in our sources, is that Swift is a static, compiler-heavy language.
Okay, what does that mean in practice?
It means the compiler is effectively your boss.
That's a great line. The compiler is your boss.
It really is. In dynamic languages, you can often get away with loose typing or handling things at runtime. You can say, I'll figure out what this variable is later. In Swift, if you fight the type system, you will lose, period.
So you have to be explicit about everything up front.
Everything. The source material emphasizes that you have to handle edge cases up front. You can't just hope for the best.
Yeah.
And look, if you embrace the strictness, you eliminate about 90% of runtime crashes before you even run the app.
Wow, 90%.
But if you try to code loosely, if you come in with that scripting mindset, the compiler will stop you every single step of the way. It will feel like you're wading through mud.
And the biggest weapon the compiler uses, or maybe the biggest hurdle for new developers coming from older languages, is the optional system.
Absolutely.
The source calls this the fix for the billion-dollar mistake. Can you break that down?
Right. The billion-dollar mistake is a famous term coined by computer scientist Tony Hoare, and he was referring to null pointers in older languages like, say, Java or C++ or.
The dreaded null pointer exception.
The dreaded null pointer. In legacy iOS apps written in Objective-C, the #1 cause of crashes was unexpectedly found nil. You try to access a variable, say a user's name, but the data hasn't loaded from the server yet. It's empty. It's nil. And boom, the app disappears. The user is staring at their home screen, wondering what happened. It's a terrible user experience.
I have seen that error message in my nightmares. So how does Swift fix this? Because things can still be empty, right? Data can still be missing.
They can, of course.
Yes.
But Swift forces you to acknowledge that possibility before you use the data. A variable isn't just a string, it's a string with a question mark.
The question mark is the key.
It's everything. It changes the type. It's a box. The box might contain a string or might be empty. You cannot look at the string without explicitly opening the box first. You have to check.
Which is what we call unwrapping.
Exactly. You have to safely unwrap the optional.
And this leads to the golden rule mentioned in the text regarding the exclamation mark.
The force unwrap. The rule is absolute. Never force unwrap. That's when you use the exclamation mark to tell the compiler, trust me, I know for a fact this value is there. Just give it to me.
It's like closing your eyes and driving through an intersection hoping no cars are coming.
That's a perfect analogy. It works, until it doesn't. And when it doesn't, your app crashes immediately. It's a hard crash. No recovery.
So is there any time it's okay?
The source is very clear on this. You should only force unwrap if you want the app to crash. For example, in a unit test where a failure means the test has failed, which is what you want. Or maybe a critical configuration error at launch, where the app literally cannot function without that data. In those cases, crashing is better than continuing in a broken state.
But for day-to-day coding?
Never. You use guardlet.
I love the visual description of guardlet in the text. It talks about avoiding the pyramid of doom.
Yes. This is all about code readability. If you use standard if-let statements to safely unwrap data, and you have, say, 3 or 4 pieces of data to check maybe a user's name, their email, and their ID, you end up nesting them inside each other.
Right. If let name, then inside that if let email, and so on.
Exactly. If name exists, then if email exists, then if ID exists. Your code starts looking like a pyramid falling off the right side of the screen. It's hard to read, and it's even harder to debug.
So guardlet flips that logic.
It completely inverts it. Guardlet allows you to exit early. You say, guard that this data exists, otherwise retain. So if the data isn't there, you bail out of the function immediately.
Oh, I see.
This keeps the happy path, the code where everything goes right align to the left margin. It makes the code readable, flat, and safe. It creates a gate at the top of your function. If you don't have your ticket, you're not getting in.
That makes so much sense. Okay, let's talk about memory. I think a lot of people coming from languages like Java, Python, or even JavaScript assume memory is just handled by magic.
The magic of garbage collection.
Right. But Swift uses ARC, not garbage collection. What's the practical difference for us as developers?
This is a crucial distinction that trips up a lot of mid-level developers. Garbage collection, which is what you see in Android with Java or Kotlin, runs in the background. It periodically scans all the memory, looking for objects that no one is using anymore, and then sweeps them up.
So it cleans up the mess for you.
It manages the mess, but it can cause little stutters or pauses when it runs. Swift uses automatic reference counting, or ARC. It's much more deterministic. It doesn't guess. It counts. It counts how many things are holding on to an object.
Like a tally counter at the door of a club?
Exactly. That's a great way to put it. If object A holds on to object B, the count for object B is 1. If object C also holds on to B, the count is 2. The moment that count hits 0, the instant the last person lets go, the object is destroyed.
Instantly.
Instantly. The memory is freed right then and there. No waiting for a garbage truck to come around.
Which sounds incredibly efficient.
It is very efficient. It keeps the memory footprint low and predictable. But it introduces a huge problem, what the source calls the silent killer, the retain cycle.
The retain cycle. This sounds like a horror movie title.
It's insidious because it doesn't crash your app.
Yeah.
It just eats your RAM. It's a memory leak. Imagine object A holds a strong reference to object B, and object B holds a strong reference back to object A.
It's a standoff, like they're pointing at each other.
It is. They're both keeping each other alive. So even if you, the developer, let go of both of them from the outside, they're still holding on to each other. Their reference counts never hit 0.
And they just stay in memory.
They stay in RAM forever until the app dies. You open a screen, it creates a cycle. You close the screen, the memory is never reclaimed. Do that 10 times, and you've leased 10 screens worth of memory. Eventually, the OS will kill your app for using too much.
And the source highlights that the most common culprit here is closures.
By far.
Closures are like blocks of code you pass around, right? Like a callback function for a network request?
Yes, exactly. If a class owns a closure, say, a callback for when a network request finishes, and that closure refers back to the class using self to update a property, boom, you've just created a cycle. The class owns the closure, and the closure owns the class.
Okay, so how do we break the cycle? The source mentions some specific keywords.
The fix is explicitly defining capture semantics. You have to tell the closure how to hold on to self. And you'll see weak self in code all over the place. It's essentially a safety net.
Explain that. What does weak self actually do inside the code?
It tells the closure, I want to look at self, the class, but I don't want to own it. I don't want to increase its reference count. I'm not going to be the reason it stays alive.
Okay.
Because of this, self becomes an optional inside the closure. You have to check if it's still there before using it, because the class might have been deallocated in the meantime.
So if the user has closed the screen and the network request finishes a second later, self might be nil.
Exactly. And that's fine. Your code just sees its nil and stops the operation. No harm done. But there's a dangerous version, too, mentioned in the notes. Unowned self.
The text calls this the speedster.
Because it's a bit faster.
Yeah.
Unowned self, assumed self will always exist. It doesn't make it an optional. It's a tiny bit more performant because there's less overhead in checking for nil.
But it's risky.
Very risky. If self gets deallocated for some reason and the closure runs and you try to access unowned self, the app crashes hard. It's a dangling pointer. You're trying to talk to memory that's already been freed. The advice here is crystal clear.
Yeah.
Use weak self unless you are absolutely 100% certain of the object life cycles.
Better safe than crashing, definitely. Now, moving to the foundational building blocks. Structs versus classes. The source uses a really good analogy here regarding photocopies versus Google Docs.
I love this analogy. It simplifies a complex computer science concept. Value types versus reference types. Structs in Swift are value types. They're like photocopies. If I have a piece of paper with data on it and I hand it to you, I'm actually giving you a complete independent photocopy.
So if I scribble all over my copy,
My original is unchanged. It's pristine. You have your own isolated world. This makes structs incredibly safe, especially in a world with multiple threads. You don't have to worry about one thread changing data while another one is trying to read it.
no one is fighting over the same piece of paper.
Exactly.
And classes.
Classes are reference types. They're like a shared Google Doc. If I give you the link, the reference to my document, we are both looking at the exact same thing. If you delete a
So
paragraph,
paragraph is gone for me too.
they're gone for everyone who has the link.
Yeah.
This is powerful, but you have to be careful. It's easy to accidentally change data that some other part of your app was depending on.
So when do we use which? Because in other languages, like Java, for example, almost everything is a class.
The rule of thumb in the source is very strict, and it's a very Swifty way of thinking. Use structs for data models, view models, and configuration. If it's just holding data, make it a struct.
So my user object, my product object, those should be structs.
Yes. Use classes for identity objects,
Okay.
things that need to be singular and shared, like a database manager, a window controller, or a network service. You don't want 5 different copies of your network service running around, each with its own state. You want one.
There was a performance nuance mentioned, though. Structs are generally fast, but what happens if they get huge?
Right. This is an important detail. Imagine a struct holding a massive raw image buffer or a giant video file. Because structs are copied when you pass them around, you might think you're duplicating 50 megabytes of data every single time you make a function call.
Which would be a disaster for performance. Your app would grind to a halt.
It would. But Swift is smart. Most of the time, it uses something called copy on write. It only actually performs the expensive copy if you try to change the data. If you're just reading it, it shares the memory under the hood. It's a clever optimization.
Okay, so it's not as bad as it sounds.
Not usually. But the source warns that for very, very large data structures, you have to be careful not to accidentally trigger that copy when you don't mean to. But for 99% of your data models, user profile settings, lists of items, simple structs are the way to go. They're safer and often faster.
Okay, let's unpack segment 2. This is where we get into what the source calls the holy war of modern architecture and UI.
It really does feel like a war sometimes. The shift in the iOS community in the last 4 or 5 years has been absolutely massive.
Let's start with how we handle time, or rather asynchronous code. We used to do this with Grand Central Dispatch or GCD and completion handlers. The source calls this callback hell.
If you've ever seen code that indents further and further and further to the right, creating that horrible wedge shape, that is callback hell.
The pyramid of doom again.
It's the same visual problem. You make a request to the server, indent. Inside that callback, you parse the JSON. Indent. Inside that one, you save to the database. Indent. Then you update the UI on the main thread.
It's a nightmare to read.
It's almost impossible to read, and error handling is a disaster because you have to handle errors at every single level of indentation. If you forget one, the app just hangs and the user has no idea why.
And the savior is async await, which was introduced in Swift 5.5.
It changes the game completely. It allows asynchronous code that waits for something to happen to look and read like synchronous top-to-bottom code. You just write the word await.
So instead of a callback block,
You just say let user await fetch user. The system magically pauses execution right there, frees up the thread to do other UI work so the app doesn't freeze, and then resumes your function when the data comes back.
And error handling.
It uses the native try-catch mechanism that Swift has for synchronous errors. You don't need complex error closures or weird enums. It reads just like a story. Try to get the user. If it fails, catch the error and show an alert. It's so much cleaner.
But then there's this new concept of actors. The source describes them as bouncers. I like that.
That's a perfect description for concurrency safety. In the old days, before actors, if you had two different threads that tried to change the same variable at the same time, say one thread is adding money to a bank balance and another is subtracting it, you got a raise condition.
And the final number could be wrong.
The final number would be wrong, or worse, the app would just crash because the memory was corrupted. To prevent this, you had to manually use things like NS-lock, which are really tricky to get right and can easily lead to deadlocks.
Where everything freezes waiting for each other.
Exactly. So enter the actor. An actor is a type. Looks a bit like a class. But it automatically protects its own state. It's like a bouncer at a club. It only lets one task access its mutable data at a time.
So it serializes the access.
It serializes access automatically. If a second task comes along, while the first one is busy, the bouncer makes the second task wait in line. You don't have to write the locking code yourself. It's a huge step forward for writing safe concurrent code.
That's huge. Now let's talk architecture. The source takes a big swing at MVC, which it calls Massive View Controller.
It's the classic joke in iOS development for a reason. In Apple's traditional design UI kit, the view controller is the center of the universe. It manages the lifecycle, it handles view did load, view did appear, all of it.
So it's a convenient place to put code.
It's too convenient. It is very, very easy for a lazy or rushing developer to just dump all the business logic, the networking code, the data formatting logic, and the database calls right into that one file.
And you end up with a single file that's 3,000 lines long.
Or more.
Yeah.
And that file is impossible to test. How do you test your networking logic if it's completely glued to the screen lifecycle? You can't. It's a mess.
So the industry standard solution now is MVVM. Model View View Model.
Correct. The source breaks it down beautifully, and it's quite simple in principle. The model is just dumb data. The structs we talked about earlier. No logic in there.
Okay.
The view is also dumb. It's just for display. It should have zero business logic. It shouldn't know how to calculate a total price. It should just know how to display a string that it's given.
Just here's a string, show it in a label.
Precisely. And the view model is the brain. It sits in the middle. It holds the state, like iLoading or the list of items. It calls the API. It takes the raw date timestamp from the model and formats it into February 1st. The view just watches the view model for changes.
And Swift UI was basically built for this pattern, right?
It was. It feels like it was designed hand in glove with MVVM. Yeah. With tools like the published property wrapper and at observed object, the glue code that connects the brain, the view model, to the screen, the view, is almost completely automated.
How does that work?
You change a variable in the view model, say you set iLoading true, and because you marked it as published, the view sees that change and reacts automatically to show a spinner. You don't have to write any code to manually tell the view to update itself. It just happens.
Speaking of Swift UI, we have to address the elephant in the room. Swift UI versus UI kit. The source calls Swift UI the future, but also calls it immature.
It's the hard truth, and you have to be pragmatic about it. Swift UI is amazing for speed of development. You can build a list screen or a settings screen in minutes, not hours. It handles dark mode, dynamic type sizes, and accessibility almost automatically.
And it's declarative.
Right. You describe what you want the UI to look like, not how to draw it step by step. But it breaks. It has sharp edges.
It breaks. In what way?
Complex navigation is still a pain point. The APIs for it have changed significantly with almost every new version of iOS. And if you need to do something very specific and custom-like, a heavy-duty layout with pinch to zoom and rotation, or a complex PDF editor, Swift UI really struggles. It hides the complexity from you, but sometimes you need access to that complexity.
And that's where UIKit comes in.
Exactly. UIKit is the old guard. It's verbose, it's imperative, you have to write a lot of code to get anything done. But it is battle-tested for over a decade. It does exactly what you tell it to do every single time. It's reliable.
So what's the strategy? Do we have to choose one side in this holy war?
No, and that's the key takeaway here. Don't be a purist. The source strongly suggests a hybrid strategy.
A hybrid.
Use SwiftUI for the leaves of your app, the
Mm-hmm.
individual screens, the lists, the forms, the detail views. It's fast and easy for those. But use UIKit for the spine, the complex navigation stack, the tab bar controller, or for any screen that needs heavy, low-level control.
And they can talk to each other. You can mix and match seamlessly. Apple provides tools for this. You can wrap an old UIKit view in something called UI View Representable to use it inside a modern Swift UI screen. Or you can put a new Swift UI view inside a UI hosting controller to use it in your old UIKit-based app. You don't have to compromise. You use the best tool for the specific job.
That's a huge relief. It's not an all-or-nothing situation. Okay, let's move on to segment 3, the ecosystem. This covers the tools, the network, and storage. First up, dependency management. How do we bring in outside libraries?
The verdict is in, and it's pretty unanimous at this point. Swift Package Manager, or SPM, is the winner.
So, RIP CocoaPods.
Pretty much. I mean, CocoaPods was great in its time. It saved us all. But it works by modifying your Xcode project files, which are Grisky. It creates a separate workspace file, and it uses Ruby. Dealing with Ruby version conflicts on a CI server is a nightmare many of us know too well.
And Carthage. Carthage is another option, but it's always been very manual. SPM is built right into Xcode. It's clean, it's written in Swift, and it's the official path forward from Apple. There's no reason to start a new project with anything else.
Okay, networking. The source warns us about the reachability lie. I found this fascinating.
This is a classic rookie mistake.
Yeah.
You want to make a network request. So logically, you write code that first checks, is the internet connected?
Yeah, that seems smart.
If yes, you make the request. If no, you show an error. It sounds logical, but it's a lie.
Why is it a lie?
Because mobile connections are volatile. They're not stable. You might have full Wi-Fi signal in the lobby when you run the check, but by the time you step into the elevator and the request actually fires milliseconds later, the signal is gone. The check said yes, but the reality is no.
So the check gave you false confidence.
Exactly. The correct advice is don't check. Just make the request.
Right.
Be an optimist. Assume it will work. And then have robust error handling for when it inevitably fails. You have to handle the failure case anyway, so the initial check is redundant and often misleading.
And speaking of failure, there's a specific pattern for the 401 loop. This is when your access token expires, right?
Yes. And handling this correctly is a real mark of a senior developer. You make a request to the server returns a 401 unauthorized error because your access token is old.
And the junior dev just logs the user out.
Exactly. They show an error that says, session expired, please log in again. That's a terrible user experience. The user was in the middle of doing something.
So what's the pro way to handle it?
You need to catch that specific 401 error code. Then you queue the original request, you put it on hold, you use your long-lived refresh token to silently hit the authentication server in the background and get a new access token. Once you have the new token, you retry the original request that failed.
And the user never even knows it happened.
They never know. They just see the data load, maybe with a half-second delay. And this logic is complex, which is why the source says this belongs in middleware. It should happen automatically in your networking layer, not in your view controller.
Sure, because if it's in the view controller, you're just going to copy and paste it everywhere.
100 times, and you'll get it wrong in half of them.
I like the tip about JSON handling, too. Snake case versus camel case.
Oh, the bane of iOS developers working with Python or Ruby backends. The API sends username with an underscore. Swift conventions demand username with a capital N. You used to have to write manual mapping keys for every single property in your model. It was tedious.
So what's the fix now?
Now, on the JSON coder object, you just set one property. Key decoding strategy .convert from snake case. And it handles it all automatically. It's magic.
That's a huge time saver. Okay, data persistence. Where do we save stuff? The source is very emphatic about what not to do with user defaults.
User defaults is for user settings. That's it. It's for flags. Did the user see the onboarding tutorial? Is sound enabled? It is not a database. It is not for storing lists of friends or chat history or sensitive data.
And especially not passwords.
Absolutely never. Passwords, API tokens, any kind of secret. They go in one place and one place only. The keychain. The keychain is a secure, encrypted database managed by the OS. User defaults is just a .plist file and XML file on the disk. If you save a token there, anyone with access to the file system or on a jailbroken phone can read it in plain text.
But the keychain API itself is kind of nasty, isn't it? It's old C code.
Horrific. It was written decades ago and it shows. The source strongly recommends using a wrapper library like Valet or Keychain Access. Don't try to write raw keychain C API code unless you really, really hate yourself.
And for the big data, like a whole database of content, core data versus Swift data.
Core data is the powerhouse. It's been around for years. It's incredibly powerful for complex object graphs, undo managers, and syncing with iCloud. But it has a famously steep learning curve.
I've heard the horror stories.
Swift data is the new kid on the block introduced in iOS 17. It's essentially a modern Swifty wrapper around core data that makes it feel native to Swift using new language features like macros. For new projects, Swift data is absolutely the way to go. It's much, much less boilerplate code.
One last thing on storage, the file manager. Never save absolute paths. Why is that such a big deal?
This burns people all the time. You save an image to disk,
Yeah.
you get the path, and it's something like users u containers my app uid 123 documents image.png. You save that exact string in your database.
Seems fine. What's the problem?
The problem is when the user updates your app from the App Store, iOS often moves the app's container to a new folder with a new UEID. The old path you saved now points to a folder that no longer exists, or worse, belongs to a different app.
So the link is broken, the image is effectively gone.
The image is still there on the disk, but your map to it is wrong. The rule is you must always construct the URL dynamically at runtime. You use the standard file manager APIs to ask the system, where is the documents directory right now? And then you append your file name to that path.
That is a no-fluff tip if I ever heard one. Let's head into segment 4, hardware and the store, or as the source calls it, the gatekeeper.
The dreaded app review.
Before we even get to the rejection, let's talk hardware. Location permissions. It's a delicate dance, isn't it?
It is. Privacy is paramount for Apple. You cannot just ask for always location access right out of the gate. The system won't even let you. You have to ask for when-in-use access first. Only after the user grants that can you later request to promote that to always.
And you have to justify it.
You have to provide a crystal clear string in your info.plis file explaining why you need the location. If the reason is vague or doesn't match the app's functionality, you get rejected. Guideline 5.1.1.
And the camera? It's not just popping up a simple view.
Well, it can be. If you just need to let the user pick a photo from their library or take a simple one, UI Image Picker Controller is fine. It's easy. But for anything professional, QR code scanning, real-time AI analysis, custom filters, you need to use the lower-level AV Capture Session API.
And the source gives a stern warning about that.
A very stern warning. The setup for the camera hardware is heavy. It takes time for the electrons to flow and the sensor to wake up. We're talking maybe 200 to 500 milliseconds.
Half a second. That's a long time in UI terms.
It's an eternity. And if you run that setup code on the main thread, the UI thread, your app will freeze solid for that half second. The user taps the button, the UI locks up, and it feels like the app has crashed. You have to do the setup on a background queue.
Now, the rejections. The source lists some common reasons people get their apps rejected. Performance seems to be number one.
If your app crashes on the reviewer's iPad, it's game over. Instant rejection. They don't debug it for you. They just send you a message that says, Guideline 2.1 performance, app completeness, and you have to figure it out.
And then there's web wrappers.
Ah, yes. Guideline 4.2, minimum functionality. This is a classic hack people try. They take their existing responsive website, wrap it in a simple app shell, which is basically just a full-screen web browser, and they submit it to the store.
And Apple hates this.
They absolutely hate it.
Yeah.
Your app must provide some kind of utility that goes beyond just browsing a website. You need to use native features like push notifications, camera integration, or offline storage. If it's just a website, they will tell you to just have your users use Safari.
And then there's the money, the Apple tag.
Guideline 3.1.1 in-app purchase. This is a big one. If you are selling digital goods, things like ebooks, online courses, subscriptions to content, or in-game currency, you must use Apple's in-app purchase system. You cannot just put a link in your app to your Stripe or PayPal checkout page.
Because Apple wants their cut.
Apple wants their 15 to 30% cut. And if you try to hide a link or sneak it past them,
They will find it.
they'll find it. And they might ban your developer account. It is absolutely not worth the risk.
So once we've navigated all that and we're ready to publish, we enter the world of certificates and provisioning. The source calls this the most hated part of Apple development.
I think that's an understatement. It is unnecessarily complex. You have development certificates for building to your local phone. You have distribution certificates for submitting to the store. And then you have provisioning profiles that act as the glue linking the certificate to the app ID and the specific devices. It's a mess of files.
So how do we manage the pain?
The best advice is Let Xcode handle automatic signing as much as you possibly can. Don't try to do it manually unless you have a very complex enterprise setup.
Yeah.
And even better, use CI/CD.
CI/CD, continuous integration and continuous deployment.
Right. Tools like the open source Fastlane or Apple's own Xcode Cloud.
Yeah.
You want to set up a system where when you push code to your repository, a server somewhere wakes up, downloads the code, builds the app, runs all the tests, securely handles the signing keys and certificates, and automatically uploads the build to TestFlight.
And that removes the human error component.
It completely removes it.
Yep.
It stops the, well, it works on my machine because I forgot to update the profile on my laptop problem. It makes the whole process repeatable and reliable.
Okay, we are deep in the weeds now. Let's go even deeper. Segment 5, Advanced Engineering. This is about scaling the system.
This is where we separate the hobbyists from the professional engineers.
Let's talk about navigation at scale. We mentioned earlier that in simple MVVM, view A calls view B. Why is that a problem when your app gets big?
It creates a hard dependency. If your login view has code inside it that says navigation controller.push home view, then the login view is forever married to the home view. You can never use that login screen in a different context, say, for re-authenticating in the middle of a purchase flow without dragging the home screen along with it. It couples them tightly together.
So the solution is the coordinator pattern.
Right. The coordinator is a separate object, usually just a plain old class. It owns the navigation controller and it manages the flow of the app. The view just says, hey, the user tapped the login button. It delegates that event up to its coordinator.
So it sends up a signal.
Exactly. The coordinator hears that signal and decides what to do next. Okay, the user logged in successfully. Now I will create the home screen and I will show it.
So the view is blind to what comes next.
Ideally, yes. Its job is to say, I don't know where we're going, I just know the button was pressed. This decouples all your views entirely. It also makes things like deep linking, jumping straight to a specific screen from a push notification, much, much easier because the coordinator can handle that complex logic without needing to load the whole UI hierarchy first.
I love that. Now here's a fact from the source that genuinely shocked me. Image downsampling. A 12-megapixel photo.
This is a memory killer, and so many developers get this wrong. A 12-megapixel photo might be, say, 3 or 4 megabytes on disk because it's compressed as a JPEG or an HEIC file.
Right.
But when you load it into your app to display it, the phone have to decode into a raw bitmap. That's raw pixel data, and that's usually 4 bytes per pixel for red, green, blue, and alpha.
So 12 million pixels times 4 bytes per pixel.
48 megabytes of RAM for one single image.
And if you have a scrolling list of them, like a photo feed.
If you have a scrolling list like Instagram, and you don't downsample those images, you will blow through the memory limit in seconds. The OS will kill your app for excessive memory usage, and the user will just see it as a random crash.
And the fix isn't just resizing the UI image object after you've loaded it.
No, because by then it's too late. The 48 megabytes are already in RAM. You have to use lower-level frameworks like Image.io to downsample the image during the decoding process. You tell the system, I know this is a 4,000 pixel wide image, but I only need a 100 pixel thumbnail for this list view. Only decode that much into memory. It saves massive amounts of RAM.
That is a crucial detail, another performance killer, off-screen rendering, specifically with shadows.
Shadows are computationally expensive. If you just add a shadow to a UI views layer, the GPU often has to switch contexts. It has to draw the view's content off-screen in a separate buffer, calculate the blur for the shadow, and then composite it back onto the main screen.
And that's slow.
It kills your 60 frames per second scrolling performance. You'll see stuttering and dropped frames. The fix is to be more explicit and set the layer. Shadow path.
The shadow path, what's that?
You basically draw a path, a rectangle or a rounded rectangle,
Yeah.
that exactly matches the shape of your view. You tell the system the shadow is exactly this shape. When you do that, the system doesn't have to calculate the alpha transparency of every single pixel. It can just cache the shape and render the shadow much, much faster.
Launch time's another big one. Users are incredibly impatient.
If your app takes more than about 5 seconds to load from a cold start, the iOS watchdog process will kill it. But even 2 or 3 seconds feels painfully slow to a user. The common mistake developers make is initializing everything in the application did finish launching with options method.
Right, they think, get it already.
Let's start the Analytics SDK, the Ad SDK, the logger, the database connection. But all of that work blocks the main thread. The user is just staring at a black screen or frozen launch image. The advice is to use lazy initialization. Wait until the first screen appears. Or do the setup on a background queue. Or best of all, wait until a feature is actually used before you initialize the SDK for it. Let the user see the UI first.
Let's talk about reactive programming. The source mentions the Combine framework. We have async await now, so why do we still need something like Combine?
It's a great question. Async await is perfect for one-off asynchronous tasks. Get this user data once. Combine is designed for handling streams of events over time.
Can you give a practical example?
The search bar is the classic example. If a user types the word Swift, you get a stream of events. S, then Swift, Swift, and finally Swift. You do not want to hit your API 5 times in 500 milliseconds.
You'd hammer the server and probably get rate limited or blocked.
Right. With Combine, you can apply an operator called debounce. It's a single line of code that says, wait until the user stops typing for 500 milliseconds. Then, and only then, take the latest value and send the network request. That kind of logic is incredibly hard to write with standard closures and timers, but it is trivial with a reactive framework like Combine.
That is powerful. Now, security engineering. We talked about the keychain, but the source goes deeper with things like SSL pinning.
This is an advanced technique to protect against man-in-the-middle attacks. Normally, your app trusts any server that has a valid SSL certificate signed by a trusted authority, like VeriSign or Let's Encrypt.
Which is usually fine.
Usually. But what if a sophisticated hacker manages to install a malicious root certificate on the user's device, maybe on a compromised corporate Wi-Fi network? They could intercept your app's traffic and read it, even if it's HTTPS. SSL pinning prevents this. You hardcode the hash of your own server's public key inside your app bundle. The app then says, I don't care if the operating system trusts this certificate. Does it match my hard-coded hash? If it doesn't, it immediately drops the connection.
But there's a huge risk there.
A massive risk. If your server certificate expires or you need to rotate your keys for any reason and you haven't updated the app with a new hash first, your app bricks itself. You'll refuse to connect to your own server. You need a backup pin or a very, very careful transition strategy. It's for high-security apps only.
Another security misconception, biometrics, Face ID or Touch ID.
Right. A lot of people think Face ID gives your app a password or some secret. It doesn't. Face ID is just a gatekeeper. All it does is answer a simple yes-no question for the system. Is the authenticated owner of this device present right now?
So how do we use it to log in or unlock data?
You store the actual password or API token in the keychain. And when you save it, you set a specific flag on that keychain item that says .user_presence. This tells the keychain, do not release this piece of data unless Face ID or Touch ID succeeds. The app never sees the biometric data. It just requests the item from the keychain. The system prompts for Face ID, and if it's successful, the keychain hands the token over to your app.
Got it. And one last security tip, screen obfuscation.
This is a small detail that shows a high level of polish and care. When you swipe up to enter the app switcher, iOS takes a screenshot of your app's last state to show in the multitasking carousel.
And if that screen shows your bank balance or a patient's medical record?
That's a security and privacy leak. That screenshot is saved to the device's disk. So what you do is you listen for the scene will raise an active event in your app's lifecycle. The moment that fires, you instantly slap a blur view or your app's logo over the entire window. When the user comes back, scene did become active, you remove it. That's very clever. Okay, segment 6, the senior mindset. This is about future-proofing and thinking beyond just the current tasks.
This is about writing code that lasts longer than the next iOS update.
Let's talk about advanced generics. The source makes a distinction between some and any. Opaque versus existential types. This is getting pretty abstract.
This is newer Swift 5.7 stuff, but it's important for performance and clarity. Some view in Swift UI is an opaque type. It means there is one specific concrete type here, but I'm hiding the details from you. The compiler knows exactly what is under the hood. Maybe it's a text view inside a padding modifier so it can optimize the layout and rendering. It's fast.
And any.
Any view is an existential type. It's a dynamic box. It can hold anything that conforms to the view protocol. Because it's dynamic and could be one of many different things, the system has to use more memory for it and dispatch calls indirectly at runtime. It's slower.
So the rule is default to some whenever you can. Yes. Use some whenever possible. Only reach for any if you really need a heterogeneous collection, like a list of different types of views stored together in one array.
Internationalization, or I18N. The source mentions a cool trick called pseudo-localization.
This is a fantastic testing tool. How do you know if your UI layout breaks in German? German words are famously much longer than English words.
Kindergarten versus preschool, Naturwissenschaften versus science.
Exactly. Your labels and buttons will overflow. Pseudolocalization is a setting in your Xcode scheme. When you turn it on, it automatically doubles all the text in your app and adds accents and special characters. Settings become settings. If your layout survives that without text getting cut off, it will probably survive German.
And RTL, right-to-left languages.
Arabic and Hebrew flip the entire user interface. The back button points the other way. Text aligns to the right. This is why in modern UI development, we never use left and right constraints. We use leading and trailing.
Ah, because in English, leading is left, but in Arabic.
Leading is right. If you code your layout using left and right anchors, your app will look completely broken in Arabic. If you use leading and trailing, the system flips it all automatically for you.
And never format numbers or prices manually, right?
Never, ever. The number 1000.00 means 1000 in the US. But in Germany and other parts of Europe, the comma and dot are swapped. It means 1.000. If you hard-code the formatting by just putting a comma in a string, you might show a wildly incorrect price to your users. You always have to use number formatter.
We have to touch on legacy code. Objective-C, it's still around, isn't it?
It will be around forever in large, mature code bases. Think Facebook, Uber, old banking apps. The senior skill here is interoperability. You need to know how to use bridging headers to make the two languages talk to each other. And specifically, you need to understand nullability.
What's that?
Objective-C pointers can always be null. Swift, with its optional system, hates that ambiguity. If you don't annotate your old Objective-C code, Swift assumes every object is an implicitly unwrapped optional, that danger cell we talked about at the very beginning.
So your Swift code is littered with potential crashes. Danger zone.
Exactly. The professional thing to do is go into the Objective-C header files and add macros like end-sysuma null begin and end-sysuma null end. This tells Swift, assume everything between these lines is not nil unless I explicitly mark it as nullable. It makes the Swift code that calls it infinitely safer.
Finally, let's define the career reality. The source draws a sharp line between a junior and a senior developer mindset.
A junior developer asks, how do I make this feature work? A senior developer asks, what happens if this feature fails? Or how do we test this? Or how will this decision affect the app in 2 years?
It's about anticipation and thinking about the failure modes.
It is. And it's about understanding technical debt. The source defines it really nicely. It's not just messy code. It's a financial instrument. It's a loan. You take a shortcut, that's the principle, to meet a deadline. But you have to pay interest on that loan later in the form of bugs, slower development, and harder maintenance. If you never pay it back, you eventually go bankrupt. The code becomes completely unmaintainable.
And the adoption curve for new tech. Do we need to rewrite our entire app in SwiftUI the day after WWDC?
Absolutely not. That's a recipe for burnout and shipping a buggy product. The industry standard is to support current OS version -2. So if iOS 18 is out, you generally need to support back to iOS 16. You don't need to chase every shiny new feature immediately. Let the technology mature for a year. Let the early adopters find the bugs in Apple's frameworks for you.
So we've covered a massive amount of ground here, from the strictness of the compiler to the nuances of memory, the architecture wars, the ecosystem, and the mindset required to survive.
We have. It's a lot to take in.
What's the big takeaway for you, if you had to summarize this whole no-fluff philosophy into one idea?
It comes down to this. The walled garden is strict, but it forces quality. The rules, ARC, strict typing, the App Store guidelines, they can be annoying, yes. But if you follow them, if you embrace them, you build software that feels native, performs beautifully, and survives for years. You aren't fighting the platform. You're leveraging its strengths.
Embrace the constraints.
Exactly. Embrace safety over convenience. Respect the architecture.
Here's my provocation for our listeners today. Look at your current project or the last feature you shipped. Are you handling the unhappy paths? We all code for the perfect scenario where the internet works and the user types in the right thing. But are you really coding for the 401 error, the nil optional, the user who steps into an elevator with no signal? Because that is where the user experience actually lives.
That's where the real engineering happens. That's the difference between good and great.
Thank you for joining us on this deep dive. It was intense, but I feel like I just leveled up.
Always a pleasure.
Until next time, keep your optionals unwrapped safely.
And your retain cycle's broken.
See you in the next deep dive.